See my screen okay? If someone can confirm.
Mm-hmm.
Great. So let's get started then. So yeah, welcome everyone to the first webinar, the first GeekGap webinar. And today the schedule is as follows. So the first part, which is about 1 hour and 25 minutes, is about algorithms and data structures. And the second part is system design. So these two parts are usually what you get in a tech job interview. And the goal of this webinar and all the subsequent ones is to help us get better at problem solving in regard to algorithms and data structures and also system design. So for the first part, we are going to talk about what is an algorithm, what is a data structure, and so on and so forth, and pretty much the same settings for the second part. And the second part will have a demo where we'll write some code in SQLAlchemy, and I will explain what that is. So without further ado, let's get right into the first part of the webinar. So what is an algorithm? An algorithm is a sequence of steps to solve a problem. So you can see it as a recipe, really. So when you want to cook, I don't know, when you want to cook a bread or you want to make some juice, you have a recipe that you follow. And at the end, when you follow the recipe well, you get the result that you're expecting. Same thing for algorithms. So for different problems, we have different ways to solve them using algorithms. So typical problems will be sorting, like you have a list of arrays and you want to sort. Another case will be searching, filtering, merging, counting, reversing a list, for example, finding a path in a graph, or compressing an image. And for all these type of problems, you have specific algorithms. So for example, here what we have on this is a simple linear search. So we have a function here, and we have a list as parameter and the target k, which we are trying to find in that list. And this algorithm literally jumps one step at the time to find the target that you're looking for, hence the word linear search. And we'll see that there are much better, efficient ways to do this, especially if the list that you get as input parameters is sorted. So what is a data structure? Again, the same analogy with cooking. If you're asked to do tea, you prefer to use something like this, or possibly if you're asked to filter something, you want to use something like that. Likewise, with algorithms and data structures, and with data structures, you are better off using some types of data structures for specific type of problem. So a data structure is a container to enable quick insertion, retrieval, update, and deletion. And in computer science, we have different types of data structures. You can have a flat array like this here. This is a flat array. You can have a linked list like this, or you can have a stack. This is a stack here. You can have a queue. This is a queue, or you can have a hash table, a hash map, or a tree, and so on and so forth. And for different kind of problems, these different data structures, like one data structure will be more uh, appropriate than the other. Same thing with the analogy with cooking. So if you're asked to drink a tea, you better use this one than here, for example. So why are algorithms? Why do we study algorithms and data structures? First of all, the applications are broad. We have loads of application. It's pretty much everywhere, everywhere. We use algorithms without knowing most of the time. And also because it helps us solve complex problems. And also one of the other reasons is for intellectual stimulation. Is really great to solve a problem and see it working. But I think the reasons why we are interested in algorithms and data structures here is for these two reasons here, because we want to be proficient programmers and pass tech job interviews. And all the companies, pretty much all of them, will require you to do an algorithm data structure and a system design interview before getting you a position. So that's why we're here mainly. So what is the structure? How do we assess good algorithms? So before, if you're asked to do an algorithm, some algorithms are good, others are not good. So how do we see if an algorithm is good or not? How do we decide? Someone is talking in the background. Let me try to can the person go on mute, please? Okay, I'm on mute. Sorry, I have to mute. All right. Okay, great. Thank you very much. So yes, here, for example, how do we assess good algorithms? Namely, if you want to assess an algorithm, you will assess the time complexity or the memory complexity. And we use a notation called the big O notation, which is a mathematical way of saying that one function grows faster than another. So that's how we assess an algorithm. So if you look at this graph here in the bottom left, this n means the size of the problem that you want to solve. And this capital case N here means the time it takes, the time your algorithms takes given the size of your problem. So some problems are constant time problems. So no matter how much the size of the input you give to the problem increases, the time it takes is constant. Others are logarithmic, this here, for example. So it's pretty much, it's not very, the slope is not very steep. Others are square roots. Some are linear. Some problems have a linear complexity. So the time it takes to solve your problem grows linearly with the size of the input, and so on and so forth. So really, you really want to be either here, here, or here, or here, starting from n squared and pulling an exponential time or factorial time. This is really, really bad. This is what you want to avoid. So really, when we assess algorithms, we want to make sure that the solution you give to your interviewer should be on this in this regime. So if you look at now at the right, we see here, for example, this is a logarithmic problem in the sense that it takes, if you look at the time it takes to iterate over this n, it's in terms of microseconds. And why? Because each time the size of the problem reduces by half. So n at the beginning, and then n divided by 2, n divided by 4, n divided by 16, and so on and so forth. So the size of the problem reduces by half every iteration, every time we get inside the loop. So this is a logarithmic problem. This is a linear problem. So here you reduce n, and then n minus 1, n minus 2, n minus 3, and so on and so forth. So this is linear. And you see, here we are already in milliseconds regime. And finally, this is a quadratic problem. Here, we do pretty much the same thing as linear, but we have a nested loop. And you can see here is 5 seconds already. And this is how you can see pretty much clearly, visually, how good algorithms affect the time it takes for your problem to be solved. All right, so now let's move to another part, which is compromising. So sometimes because we are trying to be efficient on both time and memory, but sometimes you have to compromise. For example, you may give up the solution that your interviewer will ask, or maybe on the job that you'll be doing, maybe you have memory issues and you want to optimize for time. Maybe you have memories deficiencies, so you don't have enough memory. So you can, in that case, you may want to trade off time in order to save memory. If it's the other way around, you will prefer to sacrifice memory versus time. And a typical example for each of these cases is, for example, for this scenario here, sometimes it's better to use an auxiliary data structure to temporarily store the data that you want um, to store the data in order to solve the problem. You will use an auxiliary data structure, and that auxiliary data structure will take additional memory. On the other hand, for some problems, in order to solve the problem efficiently, memory-wise, you have to sort the data first. And sorting, like we will see in one of the webinars, the subsequent webinars, sorting is an n log n problem. So you could have, if you didn't sacrifice, if you want to save memory, you may want to solve the problem first in order to achieve that. So you have to compromise, literally. Switch. Okay. So now, what is the structure of an algorithm, of an interview? Typically, a technical interview will go like this. And after this, I will jump into the use case, which is binary search. So usually you have a problem statement given by the interviewer, and your task is really to understand your problem very well. So you do that by asking questions. You have to ask questions. And we will see a use case for that. After you have asked your question and got a good understanding of the problem, you want to test your understanding of the problem by, this is your problem, and you want to give some input to your problem and see the output mentally and see if you have understood it properly. Third, you want to test the edge cases, because for some specific type of inputs, you have to handle them in a specific way. For example, for sorting or searching, what if the list that you're giving as an input parameter is an empty list? What if it's an empty list? How do you handle this kind of cases? What if it's a list with just one element? How do you handle that? This is an edge case. And fourth, what you want to do is suggest a brute force algorithm. So naive implementation, you want to give a naive implementation first. You don't have to code this. You just have to tell the interviewer, this is what I think, this is the obvious way we can solve this problem. And then at the fifth step, you point out the issues with the naive implementation of your problem. So your naive implementation may be using brute force, maybe an n square, it may be an n square, big O of n square problem, but it's maybe the case because you're not using the right algorithm, or you're not using all the assumptions that were given in the problem. And finally, at the sixth step, what you want to do is actually now write the code for the improved solution to the algorithm that was given. And finally, at the seventh step, you want to assess the time and memory of the solution that you have provided. And without further ado, let's get into our use case for this first webinar, which is binary search. And it seems like an easy thing, but really binary search is a problem that had a buggy implementation for a long time, and it's easy problem, but quite hard to get it right because there are some bugs that are very frequent, and we'll talk about them as well. So first, the problem statement is, given an array A of numbers sorted in increasing order, as you can see here, it's an increasing array. Implement a function that returns the index of target K if found in A and -1 otherwise. So here at the first step, like we said, you want to ask specific questions to the interviewer. Is there a specific time memory complexity he or she is looking for? For that question, he may say, I want the best algorithm, give me the best solution. Because telling you the complexity may be a big hint as to how you're going to solve the problem. So he may just answer, give the best you can. What is the type of input parameters? He may say, It's a list of integers, list of ints. Can we assume that they're always valid? Yes, we can. We can assume that we won't give a list of strings to the problem because otherwise your solution may not work. Also, are you allowed to modify the array in place? By in place, I mean for some problems you may be required, for example, to sort. Let's say you have 2, 3, and 1. Some problem, like I said earlier, in order to solve them efficiently, sometimes you are required to sort them first. And maybe that's a constraint that you're not allowed to do by the problem. So you have to ask your interviewer if you're allowed to sort the problem, to modify the input parameters, because depending on that as well, the solution may be completely different. And the question you ask yourself is it similar to something that I've seen before? And for this, really, the answer is yes or no. We haven't done binary research, we have just seen linear search, which is a searching algorithm as well. So that's why we say yes and no. So let's go here now. The second step is you want to give some input parameters to the problem and test the output and a couple of inputs and outputs. So let's see if this array, let's say the array is the one that we have here, and let's say k equals to 8, what should we return? If we have a and k, what should we return as output? We can return 2, we can return 1, because this is 2 here, this is the index, 2 and 1. These are valid answers. So if you have a k equals to 40, we want to return 8. If we say a and k equals to, let's say 17, we don't find 17 anywhere here, so we say -1. So this, by doing this little exercise, which seems trivial, you really test your understanding of the problem. And maybe this problem seems easy, but when we progress down the road, you'll see that it's really when doing this that you actually understand the problem that was given to you. And let's now see some edge cases. What about a equals an empty list and k equals 1? What do you return? You want to return -1 because there's nothing here. What if, because sometimes this is an edge case, if your algorithm is not implemented properly, it won't be able to handle empty list. Likewise, if your array is of size 1, and we will see that one of the bugs in binary search usually ignores arrays of size 1. If you have like this k equals 1, you want to return 0 because this is index 0. And if k equals 2, you want to return -1 because it's not there. So these are edge cases that you want to consider when doing this problem. So now, what is the brute force solution? Now, after you have done this, the interviewer wants you to give the brute force solutions. So the brute force solution that we saw earlier is literally linear search. So in a sense, we have a list of sorted list of integers, but we want to search for an element in it. So you have to start here at 0 and then at 1 and so on and so forth. This is literally what this for loop here is doing. So we start from index 0, we test if it's equals to the target, and then we move on to the next one, and so on and so forth. So that's why when we reach at position 15, we return 3, because this is 0, 1, 2, 3. And for 100 is not there, so we return -1. But this is not ideal. This is not efficient. Why? Because really, you're not using all the assumptions, like said here. You're not using all the assumption of the inputs. This is something you have to check carefully. You're not using all the assumption. One of the assumption of the input is that it is a sorted array. So a linear search is not ideal. It's pretty much like you are asked to search for a word in a dictionary, And remember, dictionary words are sorted from A to Z. So if you're asked to search for the word that starts with Y, you don't start from A and then B, all the words with B. You start somewhere near the end because you know that the dictionary is sorted. So you start from where you have the chance to find the word faster. So this is why this is not efficient. And by the way, the complexity of this algorithm is linear. So it's linear time. But we can do better. We can do better. Remember, linear is something like this, and we have logarithmic data like this. And for this, we can really have an algorithm that solves this problem in a logarithmic time. And let's see how. Let's see how with this diagram here. So first, let's say we have A equals to, sorry, let's say we have,
here are matches for equal.
Let's say we have A equals to this array, and we have K equals to 15. So let's start from here. So binary search, literally, what you do is you have 0 here and you have 9 here. You take the middle, you look at your right, is 15, can 15 be on my right? No, because 19 is already on my right. And I know because the array is sorted that everything going forward will be bigger than 15. So I just have to look this direction instead. So I just have to look this way. So now this part of the array is discarded. I just have to search this section. I do the same thing. I split again in the middle like this, and I look on my right. I see, oh wow, I can see 8. So okay, I can discard this part because I can see that 8 is here. Oh, I can, what am I saying? So we are looking for 15, not 8. So 8, I look at my right and I see that it's 8. And I know that because 8 is here, everything on my left will be smaller. So I can discard everything that is here. So now I'm left with just this part of the array. And I do the same thing. I split again like this. And I look on my right and I see that, I look on my left and I see that it's 8. So I know that I can ignore this part and I can just look this side. And finally, I split here again because now I have an array of size 2. I split here and I look on my left and I find 15. I'm happy because I found a solution. So let's do the same experiment with something that is not in the array. So same experiment. We look on the right, we split on the middle. We look on the right, it's not possible because 19 is there. 19 is bigger than 17. So if 17 is there, it's definitely on the left. What do we do now? We look, now this is 0, this is our left, and this is our right, and this is our middle. We split here again. We are looking for 17, remember. So 8, this is 8. So everything on my left will be smaller than what I'm looking for, definitely, because 8 is already smaller. So I have to look on the right. Same thing. I look on the right, and then I have to take the middle here. So now at this point, this is left, this is right, and this is middle. And I split here, and I have to look at 17. So I do the same experiment up till the point where I have an array of size just 1, and that array of size just 1 is 16, which is not equal to 17. So this is a miss. I've not found the target. So 17 is not in the array. So I have to return -1. And let's see how we are going to implement that in Python very quickly. So this is how you're going to implement this. So def binary search A, and you're looking for K, the target. What you do is you initialize your left and right boundaries like so. So your left, you want to start at 0, and your right, you want to start at the length of your array -1, because remember, indices starts at 0 in Python. So this is an array of size 10, so it goes from 0 to 9. So that's why we do len minus 1 here. And what do we do now? We have a loop. We can loop while left, and I'll introduce a few bugs consciously, and we are going to solve them later on. Okay, so now I have to iterate while my left is bigger than my right. Why this variable is bigger than? Because at some point your left is going to cross, because what is happening is, as the more you progress, left is moving this direction and right is moving like this. So at some point, left is gonna cross right. At some point, if we don't find the item, left is gonna cross right and become bigger than right. And that's the time when you know that you have not found what you're looking for. So we compute the middle. We do left plus right, integer division by 2. And what we do now, we look on the right. If k is smaller, if a mid, sorry, if a mid smaller than k, our target, what do we do? So it means that what we are looking for is on the right. So we have to shift left like so. So left becomes mid plus 1. So when we are in this regime, it means that our target that we are looking for is on the right. Else if a mid less than k, what do? We do right equals mid minus 1. Otherwise, else, the only possible case now is really if a mid equals to k. What do we want to do? We want to return mid, because this is, if a mid equals to k, then we want to return mid because that's the position where it is. And if we are out of this while loop, it means that left has crossed right and we haven't found what we were looking for. So we return -1. So that's it. That's the binary search implementation with 2 bugs that we're going to discuss later on. And here you can see the code. This is how it looks in Python. It's a bit cleaner here, as you can see. And now what we want to do at the 7th step, remember, we want to assess the time and memory complexity of the solution. And like we saw here, every time at every step, the size of the problem reduces by half. So here we started with the problem of size 10, and here we have just 5. Here we have 3, here we have 2, and here we have 1. So the size of the problem decreases by half every time, every step. So this is a hint for us. As you can see here with this array, we start with this array of this size, and then this is the initial size. Then at the second step is n divided by 2, and n divided by 4, and so on and so forth, up to the point when you have an array of size just 1. So how many steps? The goal for us is to compute how many steps does it take for us to reach this n in the worst case, because in the worst case, we have to reach the size n to say if the array the target is in the array or not. So the solution is n. What is n? Equals 1. So let's say n divided by 2k, because this is growing 2, this is 2 power of 2 here, and this will be 2 power of 3, and so on and so forth. Up to some point it will be 2 power of k, and that 2 power of k will be equal to 1. And this is the number of steps, because this is 2 power of 1. You can see this one here. This is the second step, third step, and the k step. What is k? So we are looking for this k here. So we can say n equals to 2k. And if you put the logarithm of 2 on both sides, you get k log 2 of 2. And this is equal to 2k times 1, because log of 2 is 2. So this is why we say we need k steps, and k being log 2 of n. This is why binary search is a logarithmic problem, and that's how we solve it. So now let's look at the bugs that we have committed, and we committed 2 bugs. We have introduced 2 bugs in our attempt to solve the problem. Let's see the first one. Let's go back here. We have 1 bug here and 1 bug here, literally. And let's see why. So let's start with this 1 bug here. So when you do the problem like this, because the right solution, remember the right solution, we have less than or equal, and this is how we compute the mid. The formula is a bit more than just left plus right divided by 2. The right formula is this, and let's see why. So when you do like this, when you do smaller than instead of smaller or equal, you're telling Python to never look for arrays of size 1. So if you look at this bug implementation, for example, if you're looking for 35, it's okay, it gives us the right answer. But if you look for 30, it says -1. Whereas 30 is really in the array. So what is going on? The only thing that changes is that we are doing minus instead less than instead of less than or equal. Same thing for 15. And if you look at this, the example is even more speaking when we give just 15 as input in the array and 15 as a target. So you can see here, it still says -1. So the problem is that when you say left strictly smaller than right, you're telling Python to never look at an array of size 1, because for an array of size 1, both left and right are equal. So for an array of size 1, when you compute like this will be equal. So this will be 0, the left will be 0, and the right will be 0. So when Python reaches here, this condition is not met, it jumps straight right here and returns -1. So this is what is happening in this bug. And for the second bug, it's an integer overflow. So in order to explain this bug, we are going to look at floats instead, because in Python 3, Python does not impose a limit on integers, but it does on floats. And really, we want our implementation to be bug-free, regardless of the underlying programming language that we're using. So what is happening? Really, these two formulas, mathematically speaking, they're equivalent, but computationally speaking, they're not. And the reason is, when you do, let's say we initialize the right with the maximum size. Let's say we had as input arrays to search things from a very, very large array. So if the array is really, really big, the right will be, at some point, will be a big number as well. And the left will be an equally big number. And when you sum 2 big numbers, when you do you sum 2 big numbers like this, the result is something that cannot be stored in the memory. It really can't fit into the memory. So that's why when you do this, you get a NaN, not a number, because here, this is like when you sum this and this, you get a number that is above the maximum of what the memory can store. That's why a best implementation is to first, because if you compute these two mathematically, you're going to get, if you reduce this, you're going to get this. But from a computational point of view, they are not equivalent, because here we first do right minus left. This gives us a small number that can fit into memory. We divide by 2, and then we add left. So doing it this way, you have a final number that actually fits into memory. So these are the two bugs that are very, very common. So if you go on an interview, if someone gives you binary search, don't underestimate the problem. It's quite sneaky. It's easy on the face of it, but it's very easy to make mistakes. So that's it for this first part. Is there any questions? We are going to see two variants of the binary search later on, but for the time being, is there any question? If someone is speaking, I can't hear. Leo, I can't hear you. Hello?
Hello, Junior.
Yes, hello.
Yeah, how are you doing?
I'm doing well. I'm doing well. Great. Are you?
Yeah, I'm great. Yeah, actually, I didn't follow it all, but the few parts I've seen, for me it's okay. Actually, this kind of binary research is true.
Yeah.
That it's the basics, but sometimes we need to revisit it. I think the explanation was great for me.
Great. All right.
For me, it's okay.
Fine, perfect. So we are gonna move to variants of binary search. Let's look at a couple of variants of binary search. So the first variant that we want to see is find the first occurrence of the target. So remember, for the binary search, as soon as we saw the item that we were looking at, we just stopped, right? So for example, let's take this array as an example. Let's take this array, and the target now is 8. What binary search will do is, binary search will return 4. Why? Because it will take the middle like this. Look on the right, it's not there. Look on the left. Oh yeah, I can see 8. So binary search is going to stop at this step, because at this step we already see the solution, kind of. So binary search is because at this point the middle is this. So but the row binary search is going to stop here. But if the question is to search for the first occurrence of the item you're looking for, you really want to continue looking left, because the first occurrence will definitely be left. So here, when we at this level, what we do is we keep track of the result that we have so far, which is what? Which is 4, but we continue looking left. And this is what this thing is meant for. So when you say right equals -1, you're telling, you keep track of what happened. So you save it in the variable res, and you keep looking left. So by looking left, I said it's really, we were at some point like this. We have left, right, and middle. And now at the next iteration, you want right to be now this. So left will stay the same, and right will become whatever was before mid. So now right is here. And we want to ignore this. So when we say move left, this is what we mean, really, because now after this is the first state, this is state 0, for example, this is state 1, when you have to look left. And this is what this piece of code is doing. So it takes the right and it turns it into whatever was before mid. So this is moving leftward. We keep doing that. So at this point now, when we split the array again into 2, this now is the value that we have. So we do the same thing. We keep that in res, and we keep looking left. We keep in res, and we keep looking left. And we continue. We split again into half, again, like this. We look left, we look right. We look at the right, at the left, we see that it's 5. So, and it's an array of size 1. res so far is what? Is 1. So at this point, we don't enter here. So at this step, this condition won't be met because we haven't, this is not 5. So what we're going to do, we are going to exit the while loop and return whatever was the value that we have saved so far, which was 1. That's why res of first occurrence returns 1 when binary search returns 4. And to see that it's really a variant, let's look at this diagram, this picture. You can see that it's just changing a few lines of code from the original version of the algorithm, and the behavior is completely different. So here you can see we are now initializing res. Here, this is one of the difference. And now, when binary search will return, finding the first occurrence requires you to keep looking left. And while you're moving leftward, you keep track of the result that you have got so far, and you finally return that. So that's the difference. And that's the first binary search variant. The second binary search variant is search a sorted array for an entry equal to its index. So let's say we have this array A here, and by the way, it has only distinct integers. So we don't have duplicates in this array. So no duplicates. And it's important, but we will see that later on. Not in this webinar, but later on. So let's say we want to search for an array, an element of this array, which is equal to its index. So we can see, for example, that this is 0, this is 1, this is 2. Oh, hang on, this is equal. So we have found that, so there is something equal to it, to its index. How can we cast this? How can we reduce this problem into a binary search problem? Well, the idea is really to subtract the arrays of indices and get another array B and find the target k equals 0. Because if A of I equals to I, it means that really, if you have an array B defined such as B equals to A, I, BI equals to, let me erase that, BI equals to AI minus I, then if you're looking for this, it's equivalent to looking for k equals 0 in this array. So this is what we are actually doing. And that's how we reduce this problem that apparently didn't look like a binary search problem into a binary search problem. So once again, when you have this B, what you do is simple. You just run the binary search, really. And this is what this implementation is actually doing here. So it's the binary search. So now what we do, we have just A as parameter. We don't have we don't have a target because the target is implicit, unlike binary search. Now what we want to do, each time we look at the difference between A and A minus A mid and minus mid. What do we do? If the difference is less than 0, if the difference is less than 0, we look on the right. This is what is happening here, for example. So, no, hang on. So if the difference is bigger, we look on the left. This is what is happening here. So when we split like this, the difference at this point is bigger than 0. So we look on the left, right? We do the same thing. We split again like this, and we check the difference. At this point, the middle is this guy here. What is the difference at this step? The difference is not in less than 0. It's not greater than 0. So it's definitely equal to 0. So we return mid, and that mid, what is 2. So that's how you find the solution, and that's how you cast this problem into a binary search problem. So once again, you can see it's just a few changes in order to achieve this problem, and on the face of it, it doesn't look like a binary search problem, what it is. So you just, instead of looking for A mid minus K, you look for the difference, like we discussed. So just two lines of code changed and completely different algorithm. So really that's it for this first part of the webinar. Hopefully it's not going too fast, but if you have questions, yeah, feel free to ask. Any questions regarding what we have covered so far? Can't hear you. Can't hear you. Oh, can you see my mouse? If someone can be unmuted. Can you see my mouse?
Yeah, I can see your mouse.
Oh, great. Okay, fine. Perfect.
But I think when you are writing stuff, sometimes it's a bit hard to follow because your pointer isn't shown on the screen.
My pointer isn't?
Like when you're writing something.
Yeah.
Sometimes the pointer isn't like they don't show you when you move to another spot. They only show you when you write on it. So sometimes if you jump from if you jump to another place, it might be hard to follow because you start writing in another place.
Oh, I see. So it's like there's a latency between, yeah.
Not really latency, but like if like previously when you were drawing on the time complexity graph, and then you were talking about the different graphs, and it was quite hard to see which graph you were referring to because
So you're talking about one of the very first slides, isn't it?
Yeah.
Yeah. Okay. Let's.
So
it was this one, right?
Yeah. So the next slide.
Yeah, this one.
So when you were trying to like bring our attention to the different lines.
Oh, I see.
Yeah, this will be better. Yeah, with the circle. Because
Okay.
previously, it's quite hard to see which one you were referring to.
Okay. So yeah, let me repeat that step then. So
I could follow, but it's just more like in the future, I guess.
Oh, okay.
I did manage to understand what you were talking about.
Okay, great. That's great. Great. So let's move to any question regarding the variance. Is that understandable, everyone? The variance of binary search that we covered. The first one here, finding the first occurrence, is that understandable? All right. What about this one? What about searching for an array equal to its index? Is that understandable? By the way, if you're speaking, sometimes you have to unmute yourself because, yeah. Okay. So we're going to move to the system design part. Is everyone on the page? You can chat, by the way. So if you don't want to speak, you can chat either privately or in the chat of the webinar. So I can see your answers. Otherwise, I don't know if I'm going too fast or the slides are showing properly. So is everyone on the page for the system design part of the interview? Of the webinar, sorry. All right. So what is system design? Really, the best definition I could find was on Wikipedia, and it's really appropriate definition. It defines system design as a process of defining the architecture modules, interfaces of data for a system to satisfy specified requirements. Such a mouthful, but it's very, when you break it down, you understand what it means. So let's say you're a software engineer in a company and you're asked to build a system, to build an e-commerce website or whatever. So in order to do that, you need an architecture. You need to design an architecture. So for example, this whole thing is an architecture. And your architecture has components. Components that this is one component, this is another one, and so on and so forth. You have different components in your architecture. And those components can be gathered as in modules. So you can have different modules. So different components that semantically are close in some way can be packaged into a module. And between different components, you have interfaces. So the interface is how your system, how one component talk to the other component. So for example, here, let's say we have a client. The client can be your mobile phone, it can be your laptop, and you hit the website. When you hit the website, this is the website here. Your request first, for most websites, your request first goes through what we call a load balancer. And a load balancer really is a component to decide which server, because really, if your website like YouTube or Google, you cannot serve all the requests that are sent to your server with just one computer, with just one machine. So you need multiple machines to serve the requests that are coming to your website. And the load balancer is the component deciding which request is going to be served, which server is going to serve which request based on the load because the load balancer is aware of the load on different servers. So it's going to decide that my request is going to be served by this web server. And internally, the web server is going to talk to, if I'm asking to view a video, it's going to talk to a view API because I'm reading. If I'm asking to, if I'm on YouTube and I want to download a video, then you can use the write API to write, because writing is actually uploading the video on the internet, and so on and so forth. So the read API, for example, is another component which talks to either the database directly to find the video that you're looking for, or talks to the cache, and we are going to see what a cache is in subsequent webinars. And you have finally at the very bottom, you have the database layer. So you have different kind of database serving different purposes. And the purpose of this first webinar is to discuss, because subsequently you're going to move up or bottom up. So for this webinar, we are focusing on this part here. We are focusing first on this part, how to design a database. That's the purpose of this webinar, and namely relational databases. So here is in a nutshell what system design is. It's really about designing how you're going to serve the requests coming to your website appropriately. And by that, you need to design the architecture right, the whole thing right. You need to design each component right. You need to design the interfaces right. So the interfaces as well need to be designed properly. And this is what makes system design. And really, the system design interview is as important as the algorithm and data structures interview, because it helps you become a proficient engineer. And really, the difference with algorithm data structures, they help you become proficient programmer. You know how to write code. But system design helps you become proficient engineer, because you know how the system works as a whole. You know how the components interact with one another. And it helps you pass the tech job interview, because if you interview with most companies, they're going to ask you a system design question at some point, definitely. And you need to be able to design something like this and explain what is happening. So, like we did for the algorithm data structures section, really a system design interview is approached best by following these 4 steps. So first of all, you want to outline the use cases, the constraints, and the assumptions of the problem that you have. So you do this by asking questions, once again, always. And by the way, the system design interview, unlike the algorithm data structures interview, is really open-ended. So you're expected to lead it. So you should do more of the talking than the person interviewing you. So you should be proactive, asking questions, suggesting alternatives, but it comes first by asking questions to understand the problem, the constraints, the assumptions. So, and when you do that, you create a high-level design. So if your problem is to draw a person, you may ask, is it a man? Is it a woman? How old is he? So when you have gathered all these specifications, you do a very quick sketch of how the solution may look like based on the specifications gathered at the first step. So if after that first step, the interviewer told you that it's a baby, so maybe that you have to draw, so maybe you want to draw something like this as your first step. Then you want to improve the core components. So now you have, let's say you have sketched this at the second step. You want to now improve the core components. So now you want to add the bells and the whistles like so. So you want to say it's a person, it's gonna need the mouth, need the nose, needs ears, and so on and so forth, need the neck, and yeah. So literally you improve, but yeah. So this is how you progress. So you first do like, this is like an MVP solution, quick, efficient, it solves the problem, but it doesn't have all the details that the interviewer is looking for. And then optimize the solution. Maybe like you can say, okay, it's going to have a hat because it's very hot, or it's going to have shoes. So at the end, you have to optimize the solution that you have proposed. So this is the 4th step. And let's see with the use case. And the use case for us in this section is to design a relational database system. So we want to design a relational database for an e-commerce store. And like we said, we want to outline the use cases, constraints, and assumptions. So what you want to start with is to ask to the interviewer, who is going to use the system? So if we are about to design an e-commerce store, the people using the system are going to be customers. So we want to talk about customers. And how many, how are they going to use it? So what are they going to do? So if it's an e-commerce store, we may expect the user to, let's say, place an order. What else? List the products, search the products. What else? Choose the delivery method, choose the delivery address, and you can go on and on, but this is how you're asking questions to the interviewer about what are the users of the system are going to do on your system, and based on that you have an idea of what are the tables that you need to create in your database. So we are not going to go through all these questions, but for some, like for this specific case of designing a database, I think the most important ones are the first 2. So who is going to use it? How are they going to use it? But later on, when we're going to talk about load balancers and content delivery network and so on and so forth, all these sort of questions are going to be relevant. But I think these questions as well is relevant for us. So what is read and write ratio? what is the expected read and write ratio. So for example, if you look at a website like YouTube, I come back to YouTube. So people watch more than they upload. So you may expect that the read and write ratio may be something like, I don't know, I just give a number like 1,000 to 1. So for 1,000 video watched, there's 1 video uploaded. So if you're designing your system, a system like YouTube, you want to optimize for reads a lot. You want to optimize the reads. You want to optimize the reads a lot because this is what the user do the most on your system. And optimizing the reads can be at the expense of the writes sometimes. Because at the end of the day, most of these problems are about making trade-offs. So if you have a system that is where you're reading more than you're writing, you may want to put a lot of effort into optimizing the reads. So this is, for example, a better way to draw what I just discussed about earlier on. And in UML, this is a UML use case diagram. So you can check that online after. It's a very simplistic way, but it helps you draw very carefully and very nicely what is the expected behavior of your system, especially when you want to design a database. So my e-commerce store, once again, you want to view the products, you want to search the products by name, and just by name, you're going to see that it's very important. You want to add products to his cart, you want to place an order, you want to choose the delivery address, and we can add more use cases. But for the scope of this webinar, let's focus on this. So what do we do next? Okay, so these are a couple of what we are asked to do is to design a database, right? So we are going to do this using the entity relationship diagram. Entity relationship diagram. Entity relationship diagram. Okay, so when we are asked to do this, what do? We have to gather what could be stored in the database because that's what we want to do. So we can store the products. We can store, sorry, let's erase this. We can store the products in the database. We can store the customers in the database. We can store the orders that he makes in the database as well. And for a product, for example, we may have, this can be an entity in our database with different attributes. We can say the name of the product, the type, the quantity available in the store, the quantity. And for the customer, we may say we have the name of the customer, we have his address. So these are based on the discussion that you have with the interviewer, based on the problem that he gave. You gather all the attributes that you, all the tables that you want to save in your database. You gather the specifications, literally. The address, what else can characterize a customer? I think it's fine. We have now the order. So an order can be placed by the customer, and an order will have the product that is related. So we can have the product ID, the product ID. We can have the customer ID because an order is placed by a customer. So you may want to know from the order who placed that order. So that's why you store this. And you have the cardinalities as well. So let's take, for example, the case of a product and a customer or a product and an order, or maybe let's say customer order. It's better. It's more intuitive. Let's take the case of customer, a customer and an order. What is the relationship between the two? And that's and this is explained with the cardinality. So a customer can place a customer, I'm reading left to the right. So a customer can place 0 or many orders. So 0 or many. An order can be placed by one and only one customer. So we read like this. So a customer can make 0 or n orders, and an order is placed by one and only one customer. So this is explained by these cardinalities here. So here we are using this one. So here, because of this 0 to many, we are going to put this symbol here like this. And this is UML entity relationship diagram. And when it's one-to-one, because it can be placed by one and only one user, one and only one customer. So we're going to put like this. So if you iterate on this, you finally get something like this as an initial design. So you create a high-level design of what you're looking for, and it's going to look like this. So again, we look at what we just discussed. So a customer can place 0 or many orders, and an order is placed by one and only one customer. Same thing for the order and the product. So not same thing really. The product, an order can have one or many products. A product can be purchased in 0 or many orders, because it's not necessarily that someone is going to buy the product. So once again, the order contains one or many products, and the product is part of 0 or many orders. What about delivery? When you order something, you want the item to be delivered, but it depends on whether if it's an online good. If it's a movie, you don't necessarily need a delivery. So that's why the relation between order and delivery is 0 or 1. So for an order, we have 0 or 1 delivery, right? Because if it's, let's say it's a movie, you don't need no deliveries for that. If it's a computer, then you need 1 delivery. And for a delivery, on the other hand, you have one and only one order. So going forward, you iterate on this, and you see also for each of these, we have the delivery address, the delivery date, and different attributes in the table. So this is what we call an ERD diagram, entity relationship diagram, and this is a UML diagram. It's important to know how to do this, because this is something that comes in interviews very, very frequently as well, especially for entry-level jobs. So now we are at the second step. We create a high-level design. So far our design is something like this. It's very minimalistic. What can we do better? So what can we improve, right? What is missing? So when you're talking about the database, you want to add things like primary keys, foreign keys, data type, like also sometimes you also have to handle association table, and I will explain what that is. So for example, for this customer ID, you want to make it clear to the interviewer that this is a primary key, right? This is a primary key. It's important because primary keys are unique. Okay, so primary keys are unique, they never change, and they are never known. And really, the primary key, if you have the primary key of a table, of an element, The primary key allows you, from the primary key, you can get all the other attributes. You can get all the other ones very efficiently. So the primary key gives you, once you know this, getting all the other ones is very quick. So you need to put a primary key here. Similarly, you want to put a primary key here, another one here, another one here. What about the foreign keys? Because we have relationships. Our entities are not just floating around, they're connected to one another. So, for example, when you are at an order, you want to know who placed that order. So you put a foreign key in the order table to reference the customer that placed that order. So this is foreign key here. So you place a foreign key because if you have an order, you want to know who placed that order. So that's why you put foreign key here. This means that this value for each row that you insert in the order table, it will be looking something like the order ID, obviously, because it's the primary key, the customer ID, which is a reference to one of the rows in the customer table. And then you have also a relationship between product and order. So you also put the foreign key here. Similarly, you have a one-to-one. This is, by the way, this is a one-to-many relationship. One-to-many relationship. This is a many-to-many relationship. Many-to-many. Because the cardinalities, once again, we have a product can be bought in many orders, in different orders, and an order can have many products, so many to many. And one-to-one, this is a one-to-one mapping. One-to-one mapping. This here, because for one delivery, you have one specific order attached to it. And for one order, you have one zero or no delivery, no or one delivery attached to it. So here as well, let's come back to foreign keys. You want to put a foreign key here to say that for this delivery, if you have a delivery, we definitely want to know which order it's attached to that delivery. So you put a foreign key. So we did this, and also you want to put a data type. So what is the type of a primary key? Ideally, you want to do it with integers. So you can say this is an integer here. What is the type of a name, of the first name? So it can be a string. Same thing for all of these. For the phone number, you can say it's a number. You can put a constraint. You can say it's a number of size 10, for example. For the delivery date, you can say it's a date. For the quantity, you can say it's a number as well. It's an integer, and so on and so forth. And once you do this, you see your ERD is getting more precise. So you deep dive. You take it. You dive into the details of each component. That's what we're doing. Then we want to see if we have missed something. So if you design a person, like here we design an e-commerce system, maybe we are missing something. And in this particular case, we really are. We really are missing something. And this is what we are missing. There's something wrong with this. The way we are handling this product quantity, there's something wrong with this. And to explain that, we have to see what association tables are. For example, product quantity only makes sense when you have both an order and a product. So you cannot say, because when the product quantity is hard-coded in the order table, it means that all the products are going to have, like all the orders are going to have all the orders that you make for that product are always going to have the same quantity, literally speaking. So in all the, like for one order, so if you have order, let's say order 1, and you have order product 1, product 2, product 3, how do you make how do you decide, how do you tell that for product 1 the quantity was 2, for product 3 the quantity was 4, for product 3 the quantity was, let's say, 1, because you only have one column to store that information. So how are you going to do that? It's not very optimized. So that's why we need what we call an association table. An association table, because we need to know. The association table allows you, let me go straight here and let's see what that is really. So the association table, like I was saying, by the way, it's the same diagram. We just added the primary keys, the types, and the association table that I was talking about. So what we did, we removed the customer ID, the product ID, and the customer ID from the order table, and we moved them into this association table here. So now you have the order ID here, and you have the product ID here, and you have the product quantity. And by doing like this, you can now save the product quantity for different products. So now with this, you have the order 1, for example. You have product 1, order 1, product 2, order 1, product 3. Because you have this table in a separate, because you abstract that relation in a different table, you can now have a quantity attached to each product, and for each pair, you can have a different product quantity. So you can have 1 here. For this pair, you can have 2. For this pair, you can have, let's say, 5. So once again, an association table in a many-to-many relationships, which is the case here. This is a many-to-many relationships. Some attributes only make sense if both the entities involved in the relation exist. So if you look like this again, I know it's a bit mind-bending to understand it, but it's very important because it always comes if you have an ERD system interview, 100% certain, most of the time, this comes. So you have to understand this. It's very, very important. So this literally allows, because with this design, to wrap up on this, with this design here, we are stuck. We cannot store this information. This is not possible. We are forced literally to have the same quantity for all the products. So if product 1 was 2, you're forced to also say that product, you're forced to say that product 2 and 3 are also have a quantity of 2, because you can always store that information once. Whereas with this design, you can save it differently for different pairs. And this is the end of the design of the core components. Now you want to optimize. You want to optimize your design. So, and by optimization, what can we do to optimize? Remember, one of the requirements was to be able to search products by name. So you want to search the products by name, right? And remember, we just did binary search. That's how the algorithms that we just did and the system design are kind of talking to one another. So because there's similar things happening here. We want to search products by name, right? That's why we want to add an index here. And by adding an index to that column, what is happening is that Python, SQL, when you will do a search on this table by name, SQL will use binary search. Technically, it will use binary search tree, but it's just binary search on a tree instead of an array. It will use binary search to search for the product you're looking for instead of linear search, which, like we saw, is not efficient. So when you put an index, if you know that you're going to query this table very frequently by filtering by the name of the product, you're better off putting an index on that column, because this will allow you to search in logarithmic time, big O of log n, instead of linear time, big O of n. So by putting an index, that's what you achieve. Second thing, remember, one thing also was to take care of what is the expected ratio between the read and the writes. Let's say for our system, we are really like, we expect that customers won't change their names very frequently, right? We expect that this, like when a customer creates an account, he won't come every day to change his first name and the last name. So these are, we can assume that here, the read to write ratio, the read to write ratio is high, right? So we are going to read this information more, the first name and the last name, more than we're going to change them. Also, on the other hand, when you're listing an order, sometimes you want to see very quickly who has done that, who did that, who made that order. If you don't have this information in this table, if you don't have this optimization here, by the way, this is called denormalization. You're denormalizing the table because you're introducing duplicates. This information here, this customer full name, can be retrieved from this table. But why on earth do we want to put it in this table as well? Well, it's because we want to be quick. We want to do reads quickly. Imagine the case where we don't have this here. So if you list an order, let's say this is not in this table. When you're listing the orders, what do you have? You have the order ID, you have the customer ID, and you have the date. So if you want to know who placed that order, you have to make a join query. You have to query this table to find the information. You have to query that table. And queries are costly, especially if all the time that you list orders, you want to know, you want to have the name of the person who placed the order. So that's why it can be better to actually like denormalize your table, your database, and have an extra column in this table to put the full name of the user, as well. So this will be like the concatenation of the first name and the last name, obviously, but this is a duplicate. So this information is already here, like I said, but we are duplicating. And it makes sense because it won't change often. Now, see the case where that information actually did change frequently. What will happen? So if every day the user comes and change his first name and change his last name, it means that for every, because you need to have consistency in your database. So if the read to write ratio is low, this is not a good idea, because every time if the user changes his first name and his last name, you have to go everywhere for every orders that was made by that user and also update this information, because remember, this is a duplicate information. So if it ever happens that the user changes his first name and last name, you also want to make sure that the database is still consistent. So you come in this order table and you have to update all the orders that the user has made, and it can be thousands of records. So this is like compromise that you have to make, but this is good to know. It's a good way. It's like denormalizing is a good way to speed up your queries. Adding indices is a good way to speed up your queries as well. So that's it for this system design part. Hopefully it wasn't too fast paced. And you can see here that the tool I'm using to do this, I'm using a tool called Lucidchart. And by using that tool, you can, when you create a diagram like this, it gives you the SQL schema, the SQL schema. So you can just, from this diagram, and we're going to show that in the demo section, you can extract this table, like this database from the tool. So it's a nice way to create databases. Like as soon as you have the ERD, you can convert it into this. And it's a very quick, very efficient way to design your database. So is there any question before we move to the demo? If you see my desktop, can you see my desktop?
Yeah.
Great. So yeah, this is what we were looking at. This is the program that I used to design this. And like I said, when you finish designing everything, you just click on export and it gives you the database that you want based on the relational database system. And it's a free tool. So it's really nice. So you can get the database here like this. But the demo that we want to look at is this system design demo. And here we want to see how, this demo is a SQLAlchemy demo. So SQLAlchemy in a nutshell is an object relational mapping tool. And what it does for you, it allows you to map, like you have an object, because in Python we talk about like classes and objects. So it's very object oriented. So you create a class, and for each class in your Python code, you map it to a table, hence the word object relational mapping. And when you look at the way it allows you to define, so for this notebook, by the way, will be shared. So you have the notebook to play around as well, and it will be on the GitHub. So you install, so the notebook is, we install the dependencies that we need. We need the Python package SQLAlchemy. We need Cycle2, which is the driver for Postgres, because I'm using Postgres as my database. And I connect to a database, to an actual database. And I created just now a database called GeekGap Webinar 1. And let's see what it is. Do you see that database? So I'm inside the database, and you can see there are no tables at the moment. So the database is still empty. I create some mapping. So I create the ORM mapping. So for example, this is a customer that we just discussed. The customer has a customer ID, first name, last name, address, email, and so on and so forth. And this is not an actual table. It's just a syntactic sugar that SQL gives you. So from this customer, you can get the orders that were placed by that customer by just calling the attribute. So if you instantiate an object from this class, you can just call this attribute, even if it's not part of the schema of the database. You can just do dot orders and get all the orders that were created by this customer. And this rep is just a Python function, magic function, to say if I'm printing an instance of this class, which of the attributes should we print? If you're printing an instance of this class, which attribute should I print? I want to print the first name and the last name. And once I create something like this, so actually I need to run this because it's not, I ran it early before. Okay, so I need to run this as well. Okay, now I import what I need and I create the customer class. You can see it's a table like that. And this is actually we have defined SQL object relational mapping. So this is the table, but this is still a Python object. It's not yet in the database. It's still a Python object. And we create that based on remember, we create the DB URI, and this engine is connected to the database that we created. But so far, we haven't created the tables. We have just created the Python objects. And once again, this is a one customer to many orders relationship. So now this is the association product order table here. And we have, again, the product ID, the order ID, the product quantity. And again, this is not a column, it's just a syntactic sugar. From the association, you can get which product is there and which product is there as well. But the reason, once again, why we need this association table is to carry the information that is needed by the association. So another explanation for what you're asking for is why this product quantity has to be in a separate table is because this product quantity is carried by this tuple, by both the product and the order. So it's carried by the association. For the product ID itself, the product ID, the quantity that we have here, is the total quantity for this product that we have in the store. And for this order, we need to know which quantity is attached to each order that we place, but we cannot have the same quantity for all the orders. So this product quantity attribute is carried by the association and not each of them individually, if that makes sense. So now we have, again, this is the many-to-many products, many products associated to many orders. And now when we create the order table, we have the one-to-many, one customer to many. So we have a mapper. Remember when we created the customer, we had a mapping, a relation mapping called orders. When we are now in the order table, we have a back reference to say back populate, order, and then products. So in the, no, sorry, I'm here actually. So the relationship between customer and order first is a one-to-many. So one customer can place many orders. So this back populates means that in the order table, in the customer table, it's called orders. The relationship is called orders, and that's what we have here. And now when you come here, the relationship at this level, customer. So when you have an order, you want to know who placed that order. That's why we have this relationship here. And now we have our many-to-many relationship between the products and the orders. But we do that via the association table like we did before, like we did in the object relational mapping tool, Lucidchart. So because of this product quantity, you have to do the relationship via a table that can actually carry the information that you're looking for, that you need to store. And finally, we have a one-to-one mapping between the order and the delivery. So this back populates means that in the delivery table, the column that we're going to create is going to call, is the relation that we're going to create is going to be called order. So from the order, you can get the delivery, if any. And finally, for, not finally, the product now. We have the product ID, the name, the product type, the quantity that is available in the store, and we need to link it to the orders. And we do that via the order, the association product order table. So when you do this, let me actually run this. Hopefully I run that one as well. Great. So now when you do this, you can see same thing. You have the table like this, and you have finally the delivery, which is a simple one. It's just delivery ID, delivery date, delivery address, and the one-to-one relationship between the order and the delivery. And we prefer, if it's a one-to-one, we prefer to put the relation, because when it's a one-to-one, you can either put the relation in the order or in the delivery. But because we cannot have a delivery without an order. So that's why we prefer to put the relation on the delivery side, because we could have had like a delivery ID in the order table, but we don't do that because from the cardinalities that we saw, the order can have no delivery if it's an online product. If it's a movie, it's a music, or an ebook, you don't necessarily have a delivery for that. So no need to have a delivery ID column in here. Whereas it's definitely important to put the order ID here, because for a delivery to exist, you need an order. And that's why we put it here. And once again, if you run this, you get the tables. Now we have just created the classes. Now SQLAlchemy, you see all the classes that we created were instantiated from this object here. And we can now create all the tables with the engine. And remember, the engine is connected to our database. The engine is what we created here, and it has the reference to our database. So now if I run this part, here, first of all, let's go to the database. You see there are no tables. So if I refresh, I won't see anything. And if I go back and I run this, you can see SQLAlchemy is creating all the tables in the database. So it will start with the customer. It will create the customer for us like this. It will create from the Python objects that we just created. It will create the product for us. By the way, it commits. So this is commit statement is very important, because it's actually persisting what you the operation, the transaction that you did. And then you create an order, create the association, and then it creates the delivery, and then it commits everything. So now if we go back here and we refresh, we can see now we have our tables created properly. They are still empty, but they are created. So we have the customer ID, first name, last name, address, etc. Delivery, order, an association table, we have product ID, the order ID, the quantity. If we go back here, now what we want to save, we want to add some products, we want to add some customers, we want to place some orders, and so on and so forth. So what we do, we create a session. We create a session to our database in order to connect to it. This session object allows us to do many things in our database. So now, remember, the product table is empty, right? If we run this snippet here, we create a couple of products, computer, a chair, and so on and so forth. We add them to the database like this, but see, if I run this, we can see product. And this is coming from that rep method that we created. Remember, this rep product, this rep. When we do rep, when we print an object, it will do this. It will say product, name, and type. And this is a magic Python. This is what Python calls magic functions. So by doing like this is what we get, because we created that rep. Now, if I do product ID, from here, you may assume that the products are already created. And by the way, we are not passing in the product ID. The product ID is created automatically for us by SQLAlchemy and inserted in the database for us. So when you do it, so why, when I run this, because I'm actually running here, why is it returning nothing? Well, it's returning nothing because so far our objects are still living in our memory. We haven't committed anything yet. So if I actually commit, you can see that it's now inserting. So it inserts the product, so on and so forth, and then it commits. If I now run again the product ID, I can see that yes, it's now able to return something, unlike here, because here it was returning none. After the commit, it's actually returning something. And look at what it's actually doing under the cover. is doing a select statement in the database where product equals parameter 1. Now I can change the quantity of my product. I think there are not enough bread, or maybe they're too much, maybe not enough. So I want to have 10 breads in my database, in my store. I change that, I commit. What is SQLAlchemy going to do? It's going to increase, so it's going to have an update query to our database and change the quantity to 10. So it's going to change the quantity to 10 and finally commit. So if I now do product for quantity, I get 10 as expected. Now, let's add some customers to our database. So I run this snippet, and again, the rep function will give us this. If I, so far again, it's not yet committed. So if I try to query anything, it won't work because we have to commit first. And after it's been committed, we have the users actually inserted in the database. So let's see what we have in our database so far. If I reload, you see the products that we added are now in the database. All of them are there. The users, the customers that we created are there as well. So you can see, but so far we have no deliveries, no orders, no association, and so on and so forth. So we have to create them as well. So we have to add some orders and deliveries. I just added orders because it's pretty much the same idea. So now I instantiate an order and I can assign a customer. So this is an object. And remember, when we had the order class, we added some syntactic sugar provided by SQLAlchemy so that when we are in the order, when you have an instance of this, we can pass in the customer. And this is precisely what we're doing here. So here I have an order. I can instantiate the attribute and pass in the customer. Now I have to create the association between the product and the order and give the quantity, because that quantity is relevant given a pair of order and product. So if I do that, I have this. Now I insert and I commit to the database. So here it is. So now you have this in the database. So if I refresh this, you have now for product 1, you have order 1 and quantity 5. And now I have also some customers added, some orders added. So now I have the order that was placed, the first order ever in the database at this time and by customer number 1. So what about querying the database? Well, we can query the database by different filters. So you have the product, you can query like this. So you call your session object, you query which table do you want to query. I want to query the products, and I want to query, and I'm hungry actually. So I want to filter by name if the product name is either fish or bread. So I filter like this and I run this and I have the products that we just created above. So you can see it gives us a list. The return is a list with product name and the type food. What if I could have, if I was hungry, I could have checked the database for everything that is there for food. I could have run this query instead of doing name equals, because I don't know, I don't necessarily, the table can have just more than just fish and bread. So I want to see everything that is food. I filter on a different column, which is the product type. I filter like this, it will return the same thing. What if I want to know all the orders that were placed by customer number 1? So you get the query on the order table, you filter by order customer equals to customer 1. And not only that, I want to order by the date, the order date. So if I run this, I get this. So you have all the orders that were placed by customer number 1 and they are returned by the SQLAlchemy. And same thing, if, for example, customer number 2 has never placed any order, so it should be an empty list. And you can see here it's indeed an empty list. So yes, that's it for this demo. Is there any question?
You don't have to add any association for the orders when you create them. You just have to add the order itself, is it? Based on your code.
Sorry?
When you create an order, you don't have to add the association for the order. You just have to add the order
Yeah,
itself.
you just have to add the order because they are already linked. So when you add the order, yes, it's already added. So you can, when you have linked them like this, you can add either of the three. You can add to the database either of the three. It will work because SQLAlchemy will insert that for you in the database. So and actually, if you try to do that, like if you try to, let's do an experiment and try to do it many times, you will see that it will complain, and that will answer your question why we cannot have many. So if we take let's take all these and duplicate them, copy cells and then paste. I'll just duplicate and do the same thing. Paste cells below. Okay, so let's create an order number 2. Okay, and then let's link it to customer 2, and then association product 2. I want to put quantity 10. Okay, 2, 2, 2, 2, and then I add the session, the 2, and then I add also association. You see it will complain. So let's run, have we run this? No, let's run this. Okay, let's run this. Okay, let's run this, and you see here it will complain. Why is that? Have we? Okay, let's what am I doing? So wait. Oh no, wait. Okay. Oh, is it the experiment that I wanted to run? Wait. Or maybe not, because let's see. Let's look at the database and see what is there. Reload. Okay, we have many things. If you look at the association, see order 2. So if I try to instead, let's say I want to put for the same product, let's say I want to, maybe this is the experiment that I wanted to run instead. So for the same product, I want different association. So we already did this. So we already had for product 1 and order 1, for order 1 and product 1, we already had an association. We cannot have something different there. So if you want to put now 100, it will complain. So if let's say this is 3, maybe this is what I was aiming for. Okay, so if you run this, okay, and then this. Oh, I have to define it here first. Okay, customer number 1. Okay, then commit. Yeah, you see, complaints. So it's definitely complaining because you're trying to, and it rolls back because you cannot have, like, for this pair, for order 1 and order 2 and product 1, like for order 1 and product 1, you already have something. So that's why we have, like, for this pair, you cannot have a different quantity. This is frozen already. So you cannot create another association which has order one and product one with a different quantity. It's not possible. So it will definitely complain. So now this is like proof by experimentation that you need like the cardinality then needs to be 1. Does that answer your question?
Yeah, it does. Thanks.
Great, great, great. So let's move back to, I'll stop sharing this and share something else. Oh no, not this, not this. Stop sharing. Okay. Great. So, do you see my screen?
Yeah.
Great. So, yes. So, unless there's any question regarding anything that we covered, this is really the end of this webinar. It was quicker than 1 hour quicker than expected, which is great. Any questions before we wrap up? Any question from you, Boris? Okay, so yeah, thank you guys. Oh, someone typed in the chat. Let me read. Okay, great. No question for me. Great. Thanks, Kevin. So, thank you all for attending the webinar. It was really great having you. The next one will be on the, I really hope it was worth your time. The slides, the video, the code, everything that all the materials will be shared on the website. You know where it is, geekgap.io. And the next webinar, we're going to see recursive algorithms. And we're going to see, like today we discussed about binary search from an iterative perspective. We did the iterative version today. Next time it will be the recursive version. And like we did today, we will have problem variants. So we are going to see a case study and 2 variants as well. And same thing, we're going to start next week. We're going to build on what we did today. So today we built the database layer, and we're going to move 1 step above. If you remember my diagram at the beginning of the session, we had that diagram which was discussing all the architecture and all the components of a system design. We're going to move 1 step above and talk about REST APIs. And for that, the case study, so today was SQLAlchemy. And to that, for having to implement REST APIs, you're going to look at the Django REST framework, which is a great framework. So yeah, hope to see you again next time. And thanks you very much for your time. See you soon. Bye.